Right. Could you please confirm if you can see the slide on the screen? Okay, good. Thank you. So today we'll continue with the concept of degenerate semiconductors. And let's just recap on this concept that we've discussed last Monday, right? So we have learned that a degenerate semiconductor is essentially a semiconductor that is heavily doped. Okay, so it is heavily doped, and when it is heavily doped, the behavior of the degenerate semiconductor is more like a metal than a typical semiconductor. Okay, so it is still a semiconductor in nature. It's just that the electrical properties is more like a metal than a typical semiconductor. And you can tell whether you have a degenerate semiconductor at hand if you know the doping level. Okay, if the doping level is equal to or more than the value of NC or NV, which is the corresponding effective density of states. Okay, if the value of NC or NV is equal to or more than, sorry, N is more NC or NV, then you already have a degenerate semiconductor. So if in the form of energy level, typically if you have your EF to be less than 3 kT away from either band H. So if you're talking about N-type, then you're talking about the distance between EF to your EC has to be less than 3 kT to have a degenerate semiconductor. And on the other hand, if you have P-type, then the EF, the distance between EF to EV has to be less than 3 kT as well. Right, so that shows the point when you start having a degenerate semiconductor. Okay, and we've also learned that if you keep increasing the doping level in the degenerate semiconductor, your EF will go into your conduction band, or it's going to go above EC or below EV. Okay, into the valence band if you keep increasing the doping level, right? So this is shown in this figure where you can see your position of EF relative to EC and EV for both cases. On the left for your N-type semiconductor, okay, your EF is now beyond EC. This is for N-type, and the right hand side for P-type, where your EF is now beyond your EV. Beyond means more than, right? So even though in this case for the P-type it's actually lower than, so more than in this case means relative to the band H, right? So even though if you talk about the magnitude, then of course it's lower than EF is lower than EV, but it's going into the valence band already, right? Or conduction band for P-type or for N-type. So in essence, you can summarize this N-type and P-type degenerate semiconductors as your N0 to be more than or equal to NC, right? NC, we've learned that for silicon, it's equal to 2.8 times 10 to the 19. And at this point, your EF will be more than your EC, okay? And if you keep increasing the doping level of P-type, where you have your P0 more than NV, your valence band will be higher than your EF, right, for this particular case. So that will be your summary. So once you have your degenerated semiconductors, the carrier density expression, which is the slide of free electrons, cannot be assumed anymore, okay, because it's now a degenerate semiconductor, and the law of mass action will no longer be applicable, so it will not be accurate anymore for you to use. A degenerate semiconductor still has far fewer charge carriers than a true metal. Okay, so this is the thing. A degenerate semiconductor still has far fewer charge carriers than a true metal. Okay, so that its behavior is in many ways intermediary between semiconductor and a metal. So anyone knows what's the level of charge carriers or magnitude of charge carriers in a typical metal? Anyone? If you talk about N, for example, density of electrons, do you know how much is the typical N in a typical metal? Can you Google search now and write down in the chat box? Coba tengok what is the typical value of N or density of electrons in a metal. You can try silver, you can try aluminium, or some other metals. Try search tengok what is the typical value of electrons. Anyone? Try search and share in the chat box so you can unmute yourself. Anyone has found any values? Azik, jumpa Azik, any value for the N in a metal? Tak ada jumpa? Anyone? Fatin? Fatin Nazira? Oh, that's too high. No, that's too high, patient. Cuba tengok, you jumpa untuk which metal tu, patient? Any other values? Selwan? Selwan? You found anything? Tak ada, yang lain tak jumpa ke? Typical metal. Typical N value in a metal. 6 times 10 to the minus 14. It cannot be minus, Sofidin. Number of electrons in a metal, it should be higher than semiconductor, right? So semiconductors, we're talking about 10, 14, intrinsic 10 to the 10. If you do 10, 14 to 10, 19. So in a typical metal, we normally have around 10 to the 21, 10 to the 22, okay? So that's typical value of carriers in the metal. And if you talk about, okay, 10 to 28, age is what I found. Okay, can you share the link in the chat box? Yeah, typically it's about 10 to 22 for the typical metal, okay? Okay, thanks, patient. Right, so when you talk about degenerate semiconductor, okay, right, thank you, Azuki. 300 Kelvin. Yeah, that's probably temperature dependent as well. When you talk about a degenerate semiconductor, the typical value of the carrier concentration is intermediate between a typical semiconductor and a true metal. Okay, so it is somewhere usually 19 to 20, 10 to the 19, 10 to 20. So degeneracy is often observed in the so-called transparent conductors. Okay, on top of your silicon or some other material, some other semiconductor materials that you can heavily dope. Obviously, you can generate a degenerate semiconductor already. But this phenomena, degenerate, is often observed in the material that we call or we classify as transparent conductors. Okay, most transparent conductors. Sorry. So, I think few of you are now working on FYPs based on perhaps this material, zinc oxide, indium tin oxide, fluorine tin oxide, or some other oxide, titanium dioxide. Anyone working on titanium dioxide, TiO2? Anyone? Adakah for your FYP? I think zinc oxide, perhaps a couple. Anyone working on ITO as well? Or devices with ITO? Adakah? I think some of you, yeah, working on this transparent conductors. So these semiconductor materials, for your information, are classified as transparent conductors. So why are they called transparent conductors? They are oxide material generally. Okay, they are oxide material. So when you talk about oxide material, is oxide supposed to be conductive in nature? Generally, is oxide supposed to be conductive? If you talk about, say, silicon dioxide, is it supposed to be conductive? Go back to your first topic last time when we differentiate between metals, semiconductors, and insulators. Is silicon dioxide supposed to be conductive? No, right? So silicon dioxide is an insulator, okay? So you will notice that when you talk about oxide, oxides are generally insulators, but there are few examples of oxide that fall into the category that we call transparent conductive oxide, okay? We call them as TCO. T for transparent, C for conductive, O for oxide. So these are the oxide materials that are transparent and conductive. So we call them as transparent conductors, and they are oxide because they are transparent, one, and they are conductive, two. So to be able to be classified as a TCO, so that oxide material has to be transparent and conductive. Okay. Then only it falls within a TCO domain, right? So examples of these materials are like zinc oxide. Well, some zinc oxide are not conductive, but it's naturally n-type. If you dope zinc oxide with aluminium, then it's going to be more n-type. So that will make it more and more conductive. Tin oxide, SNO2, or indium tin oxide are the examples of these TCO materials, or transparent conductive oxide, or transparent conductors, if you like to call it, right? So why do we want degeneracy in transparent conductors? Because we want them to be conductive despite being an oxide, right? And the typical doping level or doping concentration in TCO is somewhere around 10 to 19 or 10 to 20. So depending on the materials and the preparation method and some other factors. But generally, it's between 10 to 19, 10 to 20, right? So this transparent conductive oxide, TCO, the examples are like what we discussed: zinc oxide, ITO, tin oxide, titanium dioxide, right? Like TiO2. As long as they are insulators, as long as they are oxide-based, but they are conductors, you can call them as this transparent conductive oxide because they don't have to be thick. They can only be very thin in the region of like 100, 200 nanometers to be already conductive, right? So that means that at that point, 100, 200 nanometers, they are still transparent in nature, okay? It doesn't have to be very, very thick. So both transparent and conductive to be able to be eligible to be called as TCO, transparent and conductive, TC, and O is for oxide. So typical thickness is 100, 200 nanometer. This TCO conducts electricity to external circuits, right? So TCOs are being used in many different applications. For example, in solar cell, in flat panel display, in LEDs, in heat reflectors, in smart windows. In fact, if you talk about smart windows or solar windows, you can even incorporate indium tin oxide or tin oxide SNO2 or titanium dioxide into your windows, plus some other semiconducting layers in order to form solar cells, right? Solar cells on windows. So in that particular case, you don't have to you don't have solar cells that are opaque. Kalau tengok kat USM sekarang kita tengah buat installation of silicon solar cells, right? Silicon solar panels. You can see all the black or navy blue panels on the roof, on the car park, perhaps ground mounted as well eventually. And we're gonna have all the system ready by June before it's completely ready to run. So in that particular case, you have opaque semiconductor material like silicon, and you cannot see through the silicon. Okay, just like what I showed to you last time. This one, this wafer. Okay, so this is an example of opaque silicon because you cannot see through the silicon, right? On the other hand, if you use the very same solar cell, but not exactly the same material on windows, you cannot afford to have the windows to be opaque because the light will not be coming into the building. So in that particular case, you have to have your windows to be transparent completely or semi-transparent at least, right? So depending on the countries. So if you stay in Malaysia, so in our case, do we want our windows to be opaque? Do we want your windows to be nearly opaque, or you want it to be very transparent for Malaysia? What do you think? If you have windows and you want to incorporate solar cells as solar windows, do you want a lot of light to come into the building, or you want little light to come into the building for Malaysia? Anyone? Okay, alrighty. So Zuki said, okay, Sofiuddin said little light. You want little light to come in. Zuki said very transparent. That means you want a lot of light to come in. Bala said nearly opaque. Okay, nearly opaque. Okay, Sofiuddin, why do you want little light to come in? Malaysia, Sofiuddin, untuk Malaysia's context. Can I unmute yourself, Sofiuddin? Let's share your perspective. Why do you want little light to come in? It could be any of these three cases, okay? Sofiuddin? Or Zuki or Bala? Zuki, why do you want it to be very transparent? Or Bala, why do you want it to be nearly opaque?
Maybe
Okay, Fatul said it's hotter in Malaysia, like a car, we want to thin it. Oh, you want to thin, okay, right? Yeah, go ahead, Bala or Sofiuddin or Zuki. You can unmute yourself. Kita discuss it.
I'm thinking like maybe we have like not only the solar cell is now like on the roof, maybe in all our devices. So it should have like our environment should have brighter. So it's easy to apply all the solar cell to instead of at the roof, it will be on our device in the future maybe.
Okay. So you want the light to come in and power your devices as well?
Yeah.
Yeah. So in that case, you want as much light as possible to come into the building and how it can be harvested on the devices as well. Yeah, that's a good idea, right? Okay. Bala or Sofiuddin?
In my case, I was thinking the solar cells usually be on roofs or windows, So
Okay.
Malaysia is usually very sunny all the time. So Malaysians
Yep.
will usually never want the sun to come inside. Usually they'll want a big cooling environment. So I was going for nearly opaque, but not 100% opaque, so they can still see if it's on Windows. And that was my logic.
All right. So that's another perspective, because it's hot in Malaysia. You don't want to purposely heat the building in Malaysia. So you want to block some portions of the light and let some light to come into the building, so that you can control, or you can regulate the temperature inside the building. So that's another perspective. Safiyuddin, if full light, not just light, but yeah, okay, yeah, same point, right? Like Bala, if full light, not just light, but also heat coming in. Yeah, if you let the whole thing to come in, then you are letting the IR component to come in as well and hit the building, right? So Fatul said trade-off between PCE, power conversion efficiency, and AVT here is average visible transmission for transparent solar cell. So Fatul is working on solar windows as my FYP student, so that's why. So this term like PCE and AVT are the parameters that we are monitoring for solar windows. Okay. So yeah, it can be either case. It can be fully transparent if you want to do something specifically. It can be as nearly opaque if you want to block the light, majority of the light from coming into the building, just like the concept that we use on our cars, right? Kita pakai kita tinted kereta so that the inside of the car is not so hot, and we block some portions of the light from hitting the inside cabin and heat up the environment, and it's going to fight with the air conditioning system, right? So yeah, it's a balance between both, really. But if you talk about countries like what, Sweden, Finland, UK, Iceland, they might want to go for completely transparent, perhaps, because they want to get more light into the building and heat up the building. In that case, they don't have to crank the heating devices a lot in order to heat up the building, because the natural light is already there with the IR component. So it's really dependent on what you want to do and locations around the world, right? So when it comes to this, so the whole point is you can actually regulate, you can customize. If you talk about this application of the generic semiconductors for solar cell application. So ini baru satu. If you talk about TVs, or if you talk about optoelectronics, sensors, or LEDs, you can really go down into the details of the TCOs for these particular devices. Okay. So what TCO does is it is a transparent conductive oxide. So it's going to conduct the current. That means it's going to bring the carriers through the layer. Then we'll bring the carriers to the external circuit for the operation. Okay. So if we talk about solar windows, for example, if you're talking about fully transparent, like suggested by Zuki, so you'll probably won't notice the presence of any solar cells at all on a window. You will just look at a typical window, but it's actually generating electricity, right? On the other hand, if you go for semi-transparent or nearly opaque, you'll probably you must notice the presence of a layer of a coating or a tint, a plastic tinted on the inside of the glass, or between double glazing windows, if you like, in order to block some portion of the light, right? Tapi kalau letak opaque on the window, then it's no longer a window. Then it's called a facade. Okay, facade. Just like if you imagine dekat fizik punya school, kalau letak dekat building tu just vertical panels, silicon base, which is opaque in nature, it can be done as well. It's just that if you put that on the wall, it works. If you put that on the window, and it's no longer a window, it becomes a facade, right? Facade of the building. So it can be done, can be integrated in many ways. And if you talk about this, if you're interested to explore more on this solar on windows or on the building, we call this as BIPV, Building Integrated Photovoltaics, right? So that includes the incorporation of TCOs and some other TCOs. You can also include this on cars as well. Imagine sekarang, or we have more and more cars coming, walaupun tak ada kat Malaysia lagi. You're gonna see later on in the next few years, solar roof on cars, ataupun solar panels on cars punya body, on the doors, on the bonnet, and on the roof. And this domain is called VIPV, macam BIPV juga, but then it's called VI, Vehicle Integrated Photovoltaics, right? So these two are apart from the typical ground-mounted solar farm or rooftop, right? So this is called BIPV and VIPV. VI is relatively new, BI is not so new, but well, quite recent, but it's not as new as VI, right? Vehicle is pretty new. So you're gonna see like Toyota Prius in Japan, and some other, I think Lightyear or some other devices, or perhaps Tesla is going to incorporate as well in the near future. So there are so many different applications of the TCO which we can explore apart from the solar cells, right? So another concept that we're going to learn in this topic is called band gap narrowing effect. We have learned this one a little bit when we talk about the effect of doping last time in the previous topic, right? So band gap narrowing effect essentially is a phenomenon that occurs when high impurity concentration causes a reduction of the band gap. So when you have a high impurity concentration, or in this case, a high doping level in an extrinsic semiconductor, you're going to see a reduction of the band gap, a slight reduction of the band gap, depending on the level of the doping concentration. The band gap reduction that we note as a delta Eg for silicon at room temperature is given by this equation. Delta Eg is equal to 22 times n over 10 to the 18 square root milli electron volt. So note that the unit is very small, milli electron volt, right? One of 1,000 of electron volt, depending on the level. Where doping is in per centimeter cube, as we discussed before. For example, for ND less than 10 to the 18, so if you talk about N-type, remember ND is for N-type, NA is for P-type. Delta Eg is less than 0.02 EV, right? So if you're talking about less than 10 to the 18, delta Eg is 0.02 electron volt, which is less than 2% of the original band gap. And the original band gap is somewhere 1.12. So it's less than 2% change of the original band gap due to the incorporation of the dopant. However, when your ND is more than 2.8 times 10 to the 19, which is the effective density of states of electrons in the conduction band, you'll be seeing the delta Eg to be about 0.12 electron volt, which is a lot bigger than the previous case, which is more significant fraction of Eg, right? So you can illustrate this in the form of this graph. Y-axis shows your band gap, and x-axis shows your doping concentration. Okay, so that's the change you're going to see in this case for germanium, right? It's for germanium. Germanium has 0.7 electron volt. Okay, so you're going to see more and more changes above 10 to the 18. Okay. Hold on, question here. 0.2 means reduced by 0.2 here means reduced by 0.12, which is the delta Eg. So delta Eg is the change in comparison to the original band gap. So that means in this case it's reduced by 0.12 in comparison to 1.12. So kalau ditolak dapat berapa? 0.12, 1 electron volt, right? Betul. So that 1.12 minus 0.12, so you're going to get 1.0, right? 1.0. So that means if the original crystalline silicon is 1.12, if your ND is above NC in this case, then you're going to see a change of 0.12 electron volt. So that means your latest band gap, your effective band gap, is now reduced to 1.0. EV. So this is the effect that we're going to see when you go for higher doping level, and this is called as band gap narrowing effect. Okay, so it was 1.12, now it becomes 1.0. So you're going to have that narrowing of 0.12 as a result of the heavy doping. Okay, and the magnitude is going to be different depending on the doping level, and then depending on the semiconductor material as well. Okay, so another concept that is equally important is called compensated semiconductors. Okay, tadi kita belajar on degenerate, and then we see band gap narrowing effect, and then another concept is called compensated semiconductors. So this concept is when you have one semiconductor that contains both donor and acceptor impurity atoms in the same region. So that means you are incorporating both. Okay, the key here is both donor and acceptor impurity atoms in the same region. So that means, say you have both N-type and P-type in the same region. Okay, at the point you can say you have ND and NA in the same region. So how is this happening? How to form that? This can be formed by diffusing acceptor impurities. Acceptor impurities means Na, right? Na, which means P-type. You want to incorporate more P-type dopants into an N-type material. Okay, into an N-type material, or by diffusing donor impurities, or by diffusing Nd into a P-type material. So before this, we have been discussing about doping doping into intrinsic silicon. So that means you started off with intrinsic silicon with Ni of 10 to the 10 per centimeter cube, and then you want to increase your doping level to one side, either to N-type, either or P-type, right? So you either go for more negative with N-type or more positive with P-type. Only one way. And you started off with intrinsic silicon, clean silicon, pure silicon. This particular case, you can actually start off with either or P-type silicon, but you can compensate the semiconductor by incorporating the opposite dopants. Maksudnya, you start off with N-type silicon, then you diffuse P-type dopants in order to cancel out the effect of N-type. So this is called compensating the semiconductor. You are actually reversing the effective, you are reducing the majority carriers, okay? So remember, what is the concept of majority carriers? What is a majority carrier? Let's recall from the previous subchapter. What is a majority carrier? How do you define a majority carrier? Anyone? We discussed this in law of mass action. What is a majority carrier in a semiconductor? Anyone? You can write down, you can unmute yourself. Let's recap so that everyone understands. Shalini, Vishalini, what is a majority carrier in a semiconductor? Shalini? Okay, Zol, electrons are majority carrier in N-type material. Okay, electrons are majority carrier in N-type material. What is majority carrier? Apa majority carrier itu sebenarnya? How do you define majority carrier? Hassan, a carrier with either more holes or electrons? Yes, but how do you simply define a majority carrier? Kalau ada orang tanya, majority carrier itu apa? What is majority carrier? How do you define it simply? Apa majority carrier? We know that in N-type, majority carriers are electrons. In P-type, majority carriers are holes. But what is majority carrier? Flow of majority carriers can conduct electric current. Yes, it is. But what is majority carrier? You are giving all the peripherals definition or the hints or around the periphery. Apa majority carrier sebenarnya? In simple term, how do you define majority carrier? We know that conduction, N-type electron, P-type holes. Tapi apa majority carrier? NA or ND is approximately equal to NI. Yes. Tapi apa majority? I want the definition. The most important thing before we discuss all these points. I'm looking for one word that supposed to explain majority carrier. Apa majority carrier itu sebenarnya? We know NP and S squared. We know it will contribute to conduction. We know that electrons in N-type, holes in P-type. Tapi what is majority carrier? Abundant dopant charge. Yes, close. Abundant dopant charges in a pure semiconductor. Not pure. Now we're talking about extrinsic, right? It's supposed to be extrinsic semiconductor, not a pure. Either you can say abundant ataupun carrier yang dominant lah, dominant carriers in a semiconductor material. So I'm looking for the word dominant ataupun apa yang dominant lah, yang paling banyak. Okay, right? So that will lead to conduction, and it can be it is electron for N-type, hole for P-type, but the very definition is the dominant carriers dalam a semiconductor material tu. Okay, then only the moment you know which one is the dominant, then only you can compensate the semiconductor. You have to know the majority carriers first, and majority is simply the dominant carrier in the semiconductor material. So if you're talking about Zol said charge carrier, yeah, charge carrier present in large quantities, which is essentially the dominant carriers, right? So if you already have an N-type, katalah you punya wafer N-type, you start off with N-type, katalah you just assume this wafer is N-type, and so N-type means the majority carriers are electrons and minority carriers are holes, okay? And we can relate them by N times P equals to Ni squared. Sekarang ni we're talking about compensating this semiconductor, this N-type. Compensating this material means you want to reverse the polarity, or you want to reduce the number of majority carriers in this semiconductor material, in this silicon, by reversing the value, ataupun reduce the value. So that is essentially what it means by compensating a semiconductor. You compensating a semiconductor means reducing the level of majority carriers in a semiconductor. Okay. Sebelum ni kita just discuss on the doping, which means you start off with intrinsic. If you want to go N-type, put more electrons in. If you want to go P-type, put more holes in, and then you're going to end up with either N-type or P-type, right? In this case, you start off with N-type, then you nak compensate, you nak reducekan majority electrons dalam N-type, up to the point that you can even inverse the polarity from N-type, you can inverse it to P-type. It can be done. So on the other hand, you can also start off with P-type silicon, and majority carriers are holes, minority carriers are electrons. You want to compensate this P-type by reducing the level of holes as majority carriers in the silicon sampai dia betul-betul compensated, and you can even inverse the polarity of the hole or P-type into N-type eventually, right? So that is the concept of compensated semiconductor. So I want you to understand the concept first. The level of change, all those stuff, that one comes later. But the whole thing is, the whole idea is you want to reduce the level of majority carriers up to a certain point, or you can even inverse if you like. And N-type, let me just finish off in 5 minutes. Sekejap lagi saya nak pergi tu sesi dengan VC tu dekat DTSP at 10. An N-type compensated semiconductor occurs when ND is more than NA, right? ND is more than NA. Let me ND is more than NA. And a P-type compensated semiconductor occurs when NA is more than ND. Okay, so that means you can already reverse the polarity of the semiconductor. If your NA is equal to ND, okay, if katalah you start off with N-type, N-type means ND or NA, the dominant carriers, N-type, are we talking about ND or NA? N-type? D, right? Good. N-type, we're talking about ND as the dominant carriers lah, right? We learn about N can be approximated to be ND because ND is way higher than NI. Kita belajar in the last class, right? When you start off with ND, and then you incorporate more Na, you incorporate more p-type into this N-type silicon, and up to the level when Na eventually equals to Nd, you are going to end up with completely compensated semiconductor, right? Which means the characteristic becomes intrinsic again, okay? Right? So when Na eventually equals to Nd, you start off dengan N-type, which is essentially Nd, kemudian you masukkan boron masuk, then you're gonna, when you add on boron into the lattice, then you're gonna effectively reduce the level of Nd, right? Electrons as a majority carrier, because you're adding more minority up to the point when they are both equal to each other, right? So at this point, it's called compensated, completely compensated semiconductor. So in this point, at this point, do we have any effective majority carriers in the lattice? No, right? Because now Na is equal to Nd. We have to now go back to the very the very start of our discussion, which is N equals to Np equals to Ni. Remember last time we talked about intrinsic? Before we move into extrinsic P or extrinsic N, we discussed about N equals to P equals to Ni, where we talk about the bonds broken and blah, 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 which essentially equals to Ni, N times 10 to the 10. So when you have your Na compensating your Nd, or Na equals to Nd, the behavior of your extrinsic N-type, originally N-type, now becomes intrinsic. And you can even reverse the polarity. Remember when last time when we talked about increasing the polarity of a certain majority carrier, we call that doping, in order to improve the conductivity, increase the conductivity, so that it becomes more conductive either for p-type or n-type. Tapi you can also use doping to reverse the polarity. Okay, tadi kita increase conductivity, sekarang kita nak reduce conductivity. That means from extrinsic, high conductivity, high doping level, whatever, then you reverse that to intrinsic, which means poor conductivity lah, right? Poor conductivity, just like as if you don't have any dopants in the lattice, right? So this is called compensated semiconductor. Compensated semiconductors are created quite naturally during device fabrication, and we're going to see later on. So it can be done during device fabrication. For example, katalah if you have, well, let me just stop here. Katalah you want to do your FYP, for example, then you want to work with intrinsic silicon, okay? Then you only have, when you go into the lab, you only have N-type silicon left in the stock. Okay, in the cassette, ada N-type je. P-type tak ada, intrinsic tak ada. But you need to work with P-type adalah P-type ada, N-type tak ada. But then you need to work with intrinsic. So what you can do is, instead of starting off with intrinsic undoped silicon, you can actually reverse the polarity by doing compensation on purpose. And you can just incorporate more dopants into the N-type wafer sampai dia jadi compensated. Then you effectively have your intrinsic wafer to work with. Okay, so this can be done as a trick as well lah. Sebab kalau you tak ada wafer, you can just compensate the semiconductor to get intrinsic instead of starting off with intrinsic. But of course, you have to control the process well in order to make sure that it now becomes intrinsic as intended. Okay, so let's just stop here. We're going to continue with the rest. Variation of EF, the doping, variation of EF temperature, freeze out, and a bit of calculations in the end, right? So is it okay so far? The concept of intrinsic, degenerate semiconductors, band gap narrowing effect, and compensated semiconductors. Okay, is it understood?
Yes, doctor.
Do you have any questions? Can everyone follow?
Yes, doctor.
All right, good. So we're going to see, we're going to do some calculations later on at the end of this topic. So we're going to do that tomorrow. So during that time, we have 3 examples. I want you to try out first. We will see the equations that we've discussed so far, n equals to nc, whatever, will make more sense, right? And how do you use the concept of EC, EF, EV, and the change in doping and all those stuff, and EF approaching EC, EF approaching EV, it will make more sense when you do the calculation. Okay, you can even tell the level of the Fermi level, for example, by doing the calculation. Okay, so if there's no question, then let's just stop here. Then I'll see you again tomorrow, 10 a.m. Yeah, bye bye. Take care. Assalamu alaikum.
Goodbye, doctor.